Happy New Year, everyone. It's 2021. Now, today I actually want to do some programming, and I want to do it, as you can see, with the camera on, a little bit different to how I normally make videos. And yeah, I just thought I would do some coding with you, just some relaxed investigations. And as you can see by the page I have open here, which is the NES Dev Wiki, I'm doing a little bit of NES emulation at the moment, which I got inspired to do by having a conversation with someone recently when I told them I don't have time to make a NES emulator when they asked about it. And then, of course, I started looking into resources to share with them, and then I started reading the resources myself, and thought, oh, I think that would actually make quite an interesting little project. And I have a small vacation from work at the moment, and I thought I would work on something that is relaxing, and this seems like a great project. So I've done a little bit of work already, and I'll show you that. I don't want to write a regular NES emulator, and also not writing in JavaScript. So it's a little bit different, but I think you'll find it interesting. I don't think the language is going to have too much of an impact on what I'm doing today. I think a lot of today is going to be reading information and processing it and trying to work out an approach for it. And I haven't really done this kind of video before, so I'm not sure how long I'll go for. I don't think I'll do more than an hour. But yeah, let's see. Okay, so the idea I have for this NES emulator, maybe it's ambitious, but the idea I have is that I want to write it in C++, and I want to run it on a microcontroller and sort of build some surrounding circuitry on that microcontroller so that it can just output VGA signals. And so I would be able to have probably a very small board that has a VGA connector, and you could plug it straight into the back of your TV or monitor, and you would have like a little NES. And the board I'm using, or I'm planning to use, is the teensy 4.1. I really apologize that I don't have a better camera set up than this, but I am working on something to get like an overhead camera, but for now this is what I've got. Now the teensy 4.1 is a really, really cool microcontroller board. It has an ARM M7 Cortex processor on it that runs at 600 megahertz. So it's quite a beast in terms of microcontrollers. And it's got a bunch of really amazing stuff built into it. I mean, for one, it has things like Ethernet built in, really fast Ethernet. I'm not making use of that, but it does have an SD card, and that seems perfect, right? You can put your ROMs on the SD card, and then you just need to plug this thing in, and then you can just put the ROMs on a certain place in the SD card, and then maybe there's a small interface to talk to the teensy to choose which game you're going to play, and then you play the game and it emulates. And that is the idea. And yeah, this is really horrible at the moment. I didn't have the right size headers, so I've just soldered a bunch of wires onto it because I started already trying to mess around with the VGA part, and so I have this board here to output VGA signals. But that's, as you might imagine, that's very tricky. It's quite timing critical, and the code I wrote was very rough. I have no idea how long, for instance, particular instructions take to execute, and it's pretty precise timing. So that's something I'm going to work on later anyway. I don't really need to get that up and running right now. But anyway, so that's the goal. And let me show you where I'm up to at the moment. So I'll move the camera around if things aren't clear. I hope this is big enough. I think it should be. Okay, so let's move a little bit around. So I'm using Platform.io or Platform.io as the sort of programming environment for the teensy, and it's so far, I mean, the setup was a little bit of a, for me, the setup was a bit of a hill to climb, although that was more to do with the fact that I had 50,000 Python installations of different varieties, and they were conflicting with each other in weird ways. And yeah, I had to just declare Python bankruptcy and just like uninstall all of my installations recently. But once I got it set up, so far it's been a really, really easy to use environment, and it takes care of loading libraries and dependencies and setting up the build process for you. And it works great. Yeah, and I get to work in my regular environment versus the teensy is, if you don't know, is a board that's like, it's basically the most powerful Arduino you can get. You program it in the Arduino environment, and yeah, it's just a sort of Arduino on steroids. But the Arduino environment is very limited, and it's actually not very nice to program in if you're used to another environment. So I can actually just do it here in my VS Code editor. Okay, so structurally, the platform I/O. Let's close some of this stuff down. This is just the configuration file, and you can see that we've got a teensy. It's using the Arduino framework. You can actually, with platform I/O, you can use multiple different kinds of frameworks. And yeah, but as far as I know, at the moment you can only program via the Arduino environment. So under the hood, it's invoking some of the Arduino tools in order to actually load code onto the teensy, and the teensy itself has some extra tools that work in collaboration with the Arduino environment, but you don't really have to interact with that. So we've got a teensy 4.1 controller board and build flags which go in to the compiler. Well, there are a bunch of different things you can pass here, different optimization kinds. You can optimize for speed, you can optimize for size, you can optimize for lots of different things. And to be honest, I haven't even started to take a look at that right now because I have no idea sort of what kinds of trade-offs I'll need to make down the way. But we'll see. So if we open up my test CPP file here, which is what I'm using to just test stuff. So I'm just running this. I'm just running this here actually, sort of in line. I'm not loading stuff onto the teensy to test it. It would be a bit of a hassle to do that with everything. So I've got this test file, and so far I have two major components. I've got the CPU, and I've got the bus. And the NES, the CPU of the NES, you may or may not know, is a 6502, or a variant of the 6502. So the 6502 or the 6502, okay. Yeah, so this is a processor from the 70s. It's not modern, it's not particularly advanced. As you can see here, it has a maximum clock rate of about 3 megahertz. So emulating that on a 600 megahertz device should be no problem. You can see it was used in various consoles, very famous consoles here, like the Atari 2600 and the Apple II, which was just a computer that a lot of people used to use. The NES Entertainment System, the NES. Commodore 64, BBC Micro, Atari Lynx, tons of stuff. It's everywhere. This chip is, it's all over the place. And yeah, so we've got the CPU, which is a 6502, and then the bus basically is an abstract class that represents the idea of, it's not an abstract class in like a abstract programming sense, but abstract in the sense that it's like, it represents the place where all the different devices connect to and talk to each other. And yeah, so the work I've done so far is I've written a CPU class. So there's a header class. Also, just sort of disclosure, I'm not a C++ programmer, obviously by trade. So I'm probably doing a bunch of stuff wrong and not in the optimal way, and Probably not in the modern way either, although I'm not sure how effective it is to program microcontrollers using like really modern template-based C++. But at the moment, I'm basically using it to, I'm using it sort of like C and then with the classes. But if anyone knows or sees anything like really awful in this and they know C++ and they feel free to leave a comment that says that I'm doing something stupid. I welcome it. Okay, so the processor, of course, if you've seen my virtual machine series on this channel, and if you haven't, you should check that out. But if you've seen that, then this is actually quite similar to this. You know, a processor, especially a very simple processor like this, and of course the virtual machine that I wrote was quite, in some part, inspired by the 6502. Processors like these, they're not extremely complex, although they are quite things of beauty if you really get into the weeds of it. And I'll show you some of that stuff. But basically, here I've got some defines, which is basically, you know, if you use this symbol in your code, it will just like dump this in its place when running it before compiling it. So these don't actually take up any real space or anything in the program. They literally get copy pasted as these. So you can even write sort of pseudo functions, they're macro functions, which expand out. We've got a bunch of stuff here that's to do with bits, and mainly it's to do with something called the status register. And yeah, so basically this class, it sort of has a few private variables which keep track of just internal mechanical stuff, as well as a reference to the bus. Basically there are a few registers. There are very few registers on this CPU. So we've got like the A register, which is the accumulator. This is where all of the arithmetic and logical operations are performed, like based on the accumulator. You have the X and the Y registers, and these are typically used as, you can use them as general purpose registers, but they're mainly used as indexing registers. So instructions that basically will refer to either the X or the Y register as some sort of offset. So if you have a memory address, it might be an offset to somewhere else. You can use that to write more dynamic programs. Then we have the program counter, or the instruction pointer, which just keeps track of which instruction we have. You'll see that that's the only 16-bit register here. So this uint8, this is unsigned integer 8 bits, so an 8-bit byte. And it's an 8-bit processor, so all of the register sizes are 8-bit, except the program counter, which is a 16-bit register, which means it can refer to a much larger address space. Then we have the stack pointer, so that is literally just the index into the stack, and that's an 8-bit register. And you might think that's strange because it's also like a memory addressing register, but the way that works is that the sort of the upper 8 bits, the most significant 8 bits of the address are fixed. They're always 0, 1, and it's only the lower 8 bits which are sort of addressable by the stack. So you actually only have 256 stack entries. So that's where you can, that's where the trade-off is made, basically. And then you have the status register, which for some reason I found seems to be referred to by P. Not really sure why P. I guess S is not used because sometimes the S would refer to the stack pointer. But P is the status register in this. And the status register basically holds a byte's worth of information about what happened in the last instruction, or what happened in previous instructions. And the information that keeps track of is whether the last operation basically returned a negative number, and that's a 2's complement negative number. So basically this bit is always a 1 if there is a 1 in the most significant bit of the 8-bit number that was returned by the last instruction, or that was processed by the last instruction. Yeah, that's the 2's complement. I have a video about 2's complement. Go and watch it if that doesn't make sense. And then we have something called the overflow bit, which is slightly confusing. But, well, it's not really confusing, but it conflicts. Well, not conflicts. You have 2 things. I'll get to it. So you have the overflow bit. This is basically referring to when signed arithmetic operations overflow. So if you add 2 positive numbers together, and because they go over 256, they go out of their 128 byte range, that means that they will overflow and it will become a negative number, even though you added 2 positive numbers together. So that's overflow. The break bit is basically used for debugging. It's like a break point. The only thing that sets this up is a break instruction. Then you have the decimal bit, which tells the processor to work in decimal mode for some instructions. And this is actually not used in the NES, so this does nothing on the NES. It's there, I've given it a name, but it doesn't do anything. The interrupt bit, that's actually the interrupt disabled bit. So when this is high, interrupts are disabled. That's what that does. That controls whether interrupts are enabled or not. We have the 0 bit, which is set to a 1 whenever the last instruction basically came out as a 0. And then the carry bit. The carry bit is used for unsigned arithmetic. That rolls over 256 bytes. So rolls over the 256th value. So if you end up with a larger number than that, it actually sets the carry bit, and that allows you to do addition and subtraction on larger numbers than 8 bits. That's how you can do kind of 16-bit or larger arithmetic in multiple steps. Because you can always, there's an instruction, and we'll see it, that refers to add with carry. And that's it. So that's what the status register contains. And this is basically setting up some bit masks so that you can manipulate the status register in a predictable way. So the status negative takes a 1 and shifts it over by 7 places. So basically you would have a number 1, 0, 0, 0, 0, 0, 0. And you can use that with ands and ors to set that particular bit or clear it. Those are done with these macros. So you can get the value of a bit by doing a bit of shifting around, and you can set a bit by doing some shifting around. And those are abstracted into these macros. So they're not real functions. There's no like call stack. Like basically wherever you use this function with the b and the I variable, it just gets expanded into this. And you can nest macros. So the assign bit makes use of both the set bit and the clear bit macros. So this just lets you program at a higher level in terms of your thoughts, but you don't sacrifice any performance in terms of the program itself. And depending on how you set your compiler optimizations up, basically tons of this will just go away, right? If the compiler knows that you have an operation where, you know, b is a known value, 1 is a known value and I is a known value, and you're doing some shift operation, the compiler will just replace that with the actual value. So it's not that you actually have to calculate these every time you use them in code. The compiler will pretty much invariably turn these into their real value. So that also helps, because it helps you mentally map this out the way that you think about it as being these shift operations and being certain positions within a bit, without having just long streams of binary numbers that you can't make much sense of. Yeah, so that's a nice thing about C++. I'm enjoying writing C++ lately. Yeah, it's been nice so far. Okay, then you have something called addressing modes. These are basically, you can, in the virtual machine we have like a move instruction, but that you can move one register into another, or you can move a register to memory. You can move a memory location to a register. And those would be the different ways in which you can do that. You can think of them as the addressing modes of the CPU. And the 6502 has a fixed set of 13 addressing modes. So, for instance, you have an instruction with no arguments. That's what's called an implicit addressing mode. You're not addressing anything explicitly. It's an implicit address. So there is an instruction, for instance, which is I think there is an increment X instruction, or an, maybe I'm making that up, I think. Yes, so for instance, something like increment X or increment Y, they work on a particular register, so you don't need to name a register. And you can't. That's not how this instruction set works. So you can increment the A register in an instruction, you can increment the X and the Y, but that doesn't become part of the instruction. So those instructions are 1 byte wide. Then you have the accumulator, so instructions that work on the accumulator. So when you're usually providing some kind of value, or the instruction itself uses the accumulator's value to do the next thing. So it's kind of like an implicit instruction, but just one that uses the accumulator. The instruction doesn't itself sort of figure out where things are. Then you have immediates. That's where like you use a literal value as part of the bytes inside your program. So you have like a load a value into the A register, and then you can provide a value right there, and that just gets compiled immediately into your program. And then there are a bunch of different things which are basically where you're using addresses, but you have different kinds. So there is an optimization for something called the 0 page. That's when you're addressing something in the first 256 bytes of memory. Those are optimized instructions. They're 0 page instructions, and you can save a byte in the program space by using these, and also some cycles in the program sometimes. These instructions that use X's and Y's, they use the X and the Y register in some way to offset this address. So basically, if you have a 0 page X addressing mode, you're providing sort of both a memory address in the first 256 bytes and let's say the X and the Y register in a way that's going to like just shift that address around a bit. Then you have relative. I believe relative is not used in that many instructions. Well, I would have to take a look to remember exactly which instructions this is used by. You have absolute, which are of course just like full 16-bit addresses immediately available. You have ones which are offset by the X and Y, and then you have something called the indirect instructions, and these are like the most complicated. These are like, you've got values where you're pointing to values in memory, and then you pull those values out, and then you manipulate those values you got from memory using the X and the Y register in some way. And the indirect is used by only one instruction, and that's the jump instruction. It has two addressing modes, and one of them is this indirect. And that's the only place it's used. But it was apparently, which anytime you're developing especially in the 70s, you're developing like a circuit, like a chip with really specific constraints. If you have an addressing mode that works on just one instruction, that's actually quite you have to really consider the idea of doing that, because it's like you're gonna waste a lot of resources. Like you want to be able to have instructions that are able to encode as much information as possible. And if you have an addressing mode that only works for one instruction, you've sort of thrown away a bunch of possible encodings that you could have. But you'll see that the 6502 actually doesn't make full use of all of its address space. Actually, it's got some sort of hidden gems in there as well. All right, and then of course, so you've got like these addressing modes, and then of course you've got all the instructions. I think there are 57 instructions if I'm not wrong. So I've got here a method for every instruction. It doesn't return anything, it's just void. And then there are some other higher level functions like connecting to the bus. So that's basically just giving our CPU a reference to the bus. That's why we have this pointer here. A read and a write function, so it can write to an address with a value that doesn't return anything, and you can of course read from an address, and that returns you an 8-bit number. These functions just abstract the same functions on the bus, so the CPU never needs to like talk to the bus directly. It can talk to its own methods about reading and writing. Then you have push and pop, which are just stack interacting write functions and read functions. So they're basically just like read and write, but only for the stack. There is a function for step, which takes a step in the CPU. So it does the full fetch, decode, execute cycle. And then there is a function that is there just to print out the state. And you can actually see that here in action. So these two lines print out, the 3 registers, the A, the X, and the Y, and then the flags named nicely. So this is the header file. This is one of the things about C and C++, which is of course quite different to JavaScript. You have header files and you have implementation files, which might seem like a really weird concept at first, but actually it's if you know the way that the compilation model works and like how different parts of the code are compiled, it starts to make more sense. It's about providing enough information to the compiler to be able to put code together, and then later you can put all the code together with all the information, and then everything will, get fit together correctly. But you can provide just enough information at different points that usually means you don't have to compile everything every time you make one change. So I'm not actually working, so I don't need to submit my hours right now. Yeah, so that's pretty cool. I'm not going to go into all of that stuff. To be honest, I don't like fully understand it well enough that I could do it justice. So, but just know that it's pretty nice to be able to split your implementation and your sort of like declaration of your interface. It's a good thing, although it does mean that you pretty much have to work a lot of the time with your 2 windows open. So like you have your header file here and your implementation file here, or at least that's how I found that it works the best for me. All right, so in the CPU implementation, what you'll see is that, oh yeah, and I have a function for every addressing mode as well. That just and then you'll see that the way that these functions are implemented is very much like the virtual machine. So there's this function step, and it gets an opcode by reading at the program counter, then incrementing the program counter. And then there's just a big switch statement that checks what the opcode is and decides what to do based on that. So of course there's just a value assigned associated with every instruction. Actually, the 6502, I really should show it. It's designed, the way it numbers these instructions it's not an accident, and there is a pattern to all of these values, and you see it as you go through and you implement them. You realize that, for instance, like ADC and here, they have the same number of addressing modes used. And if you look at the relative difference here, we have like 6.9 and we have 2.9, and then we have 6.5 and we have 2.5, and then we have 3.5 and 7.5. And these things are exactly the same distance away, and that's not a mistake, and it's not an accident. That's part of the design of the instruction layout and the way that the processor actually decodes the instructions. So I'm representing numbers here as hexadecimal, but these are just bit patterns, right? So the number is 8 bits wide, and the patterns of those 8 bits define the way in which the processor works. I actually think it's nice to show at this point, maybe in one of these tabs I have it open. As you can see, I've been working quite a bit on this. The different addressing modes and things open. Okay, so I don't have a tab open, so what I'm going to do is I'm going to say 6502 opcode table. Can't see what I'm writing now. DuckDuckGo, not the best for to opcode table. actually can't see what I'm writing. There are some really, really nice diagrams of this some places. And this is not where I'm finding them. Let's take a look. I know I had a nice document open somewhere. Oh, here. Yeah, so this is not exactly the one I was thinking about, but you can see here we've got like this is the low nibble, so this talks about the number on the hexadecimal number on the right hand side of the byte, and this refers to the most significant nibble on the left hand side, and this forms a table of instructions. So at 0, 0 you have the break, at 1, 0 you have a BPL relative, branch. This is based on some sort of flag, and I remember that the PL didn't really have a accurate corresponding to the actual instruction. I remember exactly what it was now. But you can see here, these things in the middle, these places, this is where just there are no instructions. So if you were to use the opcode 02, there is no documented instruction for what 02 does. As far as, you know, the read the manual is concerned, there is no 02 instruction. The whole 7 column is just empty, as is the B column. But you can see here actually that things are laid out in a certain way. Like things are laid out in a pattern. And now there is actually, the interesting thing is there are actually instructions here. Every one of these does something. And what they do is, because of the way that the decode logic works, basically, you know, looking at the decoder, basically, you can see that it must be just looking at rows and columns at times. So, you know, you see that in this column, you can see that these are all instructions which are related to using the indexing registers, like the X and the Y. So that's just part of the decode logic, that if there's a 1 here on the left side, then it's going to be to do with the X and the Y registers. You can see here that, does this work quite as well? You can see here that all these things that say ZPG, these are 0 page related. So things here may or may not be related to the 0 page. The decode logic is really smartly laid out in a geometric way, so that you can decode your instructions. But the really, really interesting thing is that there are a bunch of instructions in these gaps, and they're not documented, and they're the so-called illegal instructions. And they do interesting things, and game developers on all the different systems, they did actually sometimes use these instructions. So if, like in my emulator, at the moment, I haven't implemented the behavior of these undefined instructions. But that means that there are some games that will never play in this emulator because I'm not properly emulating the behavior that was actually there in hardware. There are, of course, these are very, very well studied, and the 6502 has been completely reverse engineered at this point. And if you search for it, you will find an amazing, like, transistor level simulation in the browser of every transistor and every gate and all the electrical characteristics. This chip has been analyzed to death. And it's amazingly interesting. I think it's a real work of art. You know, it's a whole different era of how chips were made. Very interesting, but really, I mean, not that I really have a goal today, but this is not really the what we should be doing. Okay, so every instruction, it's got all of its different addressing modes, and basically what it does is it makes a little case statement for every one of the valid instructions, and first calls the addressing mode that's related to that, and then it returns with the instruction. So the instruction code is always the same, no matter what the addressing mode is, because the instruction will always behave the same. It's always taking some kind of input and producing some kind of output. And it's actually the addressing mode that defines, for instance, which value you're working with or which address you're working with. And that always works the same as well. So that logic just lives somewhere else, and the instruction logic itself lives in a different function. And I will show you very briefly how these look. We'll pick one that's a little bit more interesting. So if we have an addressing mode of immediate, what we're going to do is we're going to say that our current address is whatever is the program counter right now. This plus plus happens after we've assigned the value. So the value of the program counter right now, that's the address. So if anything is going to do something with the current address in the immediate mode, that's what the address is. The current value is whatever is at that current address in memory, or not memory, but whatever is connected to the bus at that corresponding location. And here we just also set the addressing mode. So there's just an enum here that lists all the possible values, and you see here that immediate is just 2. It's just the value 2. But that has no real significance. This is really only in the emulation terms. Oh, my tea is cold. Okay, and then there are 0 page, and they all do the same thing, and some of them are more complicated. So for instance, if I have a 0 page with X, basically what that means is like, read the value in the program counter, that's the current address. That's basically, if you think, so you have to think about how this looks, right? If we have some memory here, so let's say we're at location 65, memory location 65, and we had like I don't know, I don't even know the exact opcode right now, but let's say we had, let's not use 65, let's say we had 2C as our instruction opcode, then we might have another value here, which is just some random byte, 55. And so what's happened is when we've already decoded this instruction. So at first the program counter, that's here, right? We decode the instruction, and that's going to move the program counter forward, right? So some instructions are 1 byte, so you just first move it forward. And then depending on the addressing mode, you're going to consume more of the memory as you go through. So now we're looking at this 55, and that's our immediate, that's our address, our 0 page address, so the 55th byte of the 0 page. And we take that, so we've read that out of memory at this address. We've got that 55 value now, so this is just 55, and then we add the X register to it. So that's it being used as an offset. So whatever is in X is offsetting this 55 value. The way that this works is that there are going to be things in that first page of memory, tables of information, addresses and things, and you're actually using the X register to point to different values in a table. So if I know that my game has a table of addresses at the address 55, and then every next byte is, or every 2 bytes, let's say, is points to another address, then you can use this X register to grab a certain address, maybe of a subroutine or maybe of just some data in memory. Yeah, so that's how and why those are used, and of course you can see how that's generally useful. All right, it continues this way, and there are some more complicated ones. For instance, the indirect instructions have quite complicated. Too big. They have quite complicated addressing modes. So there are even yeah, it's quite a tricky thing. So like here, for instance, we read whatever is at the program counter, we add X to it, and then we make sure that that is a uint8t. We're casting that explicitly. I actually think this would, since the program counter and this read return uint8t and the X is uint8t, I don't think that this is actually strictly necessary. so you see here, we first read that, and then we read the byte next to it. So just whatever was at the program counter plus x plus 1, which could overflow, and that's maybe when we eventually start writing code, that we'll get to that. Then we're going to AND those together. I actually think there's a bug here, because I think this gets shifted and then ANDed. Yeah, I think this is correct. I need to check the operator precedence here, because I'm not sure if this AND operation is going to happen first, or if this shift operation. I think the shift operation, to be honest, I'm just going to put the brackets there because I don't know. But basically you can see we're forming a 16-bit number here. We're putting something in the low 8 bits, and then we're reading something else, and then we're shifting it to the high 8 bits. So we can make ourselves a 16-bit number out of 2 sequential addresses. And this is how the 6502 works when it's looking for like 16-bit addresses in memory. It has to do 2 memory lookups. And everything is documented as the number of CPU cycles that it takes. So I think here, if I look, this is what I actually use to implement all the different instructions alongside some other resources. But basically, every instruction in this page tells you the name. It tells you which processor flags are affected by this. It gives you a little description. This sometimes is not enough, or at least I found it wasn't enough, and I had to use some other resources. And it tells you that based on which different addressing modes are used by, and also the opcode. So you have all the information here you need. And it tells you how large that instruction will be and everything. And you can actually, I think you can imply, based on addressing mode, you will just know always, like, it's never that you have an absolute X addressing mode instruction that isn't 3 bytes, I think. No, actually, I don't think that's true. Oh, maybe it is true. Maybe it's true byte-wise, but it's not true cycle-wise. So these are the number of CPU cycles it takes to get through a single instruction. You can't do everything in a single CPU cycle, especially if you're talking to memory. That takes time. And you can see here that they get sort of more and more the more complex your operation is. And if you're doing an indirect X, which I think is what we were just looking at here, indirect X. If you're doing this operation, which you can see takes like 1 read, 2 reads, 3 reads, 4 reads, 5 reads, you know, you're adding up in the number of memory reads you need to do. Yeah, that adds up, and you end up taking 6 clock cycles to execute this instruction. So the number of clock cycles that things take, that's actually done in the instruction at the moment. Although, as you'll see, that's something I need to fix, because sometimes the addressing mode has an impact on that. As you can see here, +1 if page is crossed. And that's, yeah, that is what I hope, if we ever start programming, what we'll actually get to today. So inside the instructions, this is how it basically looks. The addressing mode has done some stuff for us. It's for instance, put something in the current value based on what instruction type we have. That might be a value from memory. It might be the accumulator's value. Yeah, could be different things. It will be one of those two things, actually. Or, yeah. Let's not look at this one because it's too complicated. Let's look at something similar, like branch if carry is set, which basically means if the carry bit is a 1, then we're going to jump to a new address, and if not, we'll continue. So it's quite a simple instruction. What it does is it checks the bit value of the carry bit in the status register, which is P, remember. This is just like in JavaScript. You can check, you know, this if anything is non-zero, or if anything is at least positive, then it's considered to be true, and if it's 0, it's considered to be false, so we can just do this. So if the carry bit is a 1, we're going to add to the program counter what we have in the current value as a signed 8-bit integer, which means we're going to use 2's complement here to represent negative numbers so that we can jump backwards if we want to do that, because you can imagine that you want to write programs that do that. But you can only jump 128 bytes around maximum with 2's complement, because you can't use all 255 bits, otherwise you would be jumping forward. 256 values, sorry. Mixing terms here. And you can see here that we've already encoded the idea that if the branch is successful, this actually takes an extra cycle than if it's not. So this instruction takes 2 clock cycles if we don't take the branch, but it takes 3 if we do. So there is some logic here to do that kind of stuff. This is quite a simple instruction. It doesn't actually set any flags, but most instructions do both check flags, they set flags, and they have to add different numbers of cycles based on the outcome. So here you can see, I won't go into how this works exactly, but here you can see we add to this instruction is add with carry. So that adds the accumulator along with a current value of some kind. So we get that from our addressing mode, and the carry bit. And the carry bit will only ever be 1 or 0. But basically this allows us to do our, our multiple byte addition, because we can just set the carry bit in some addition. At first it should be empty, so we have an empty carry bit. Then we'll add something together. It might carry over, and then we'll add another byte using the carry bit, so we can sort of ripple that addition through. I'm not sure if that's clear, but the best we'll get for now. This assigns a bunch of flags to the status register. So we're assigning here the overflow bit based on this complicated looking bit shift, which took me some time to write. I really had to look in a bunch of places to make sure I got this right, because it's it's a bit tricky to wrap your mind around. So yeah, sometimes if you come across a piece of code like this, and you think, oh, it's a really short piece of code, I must be so stupid if I can't read this at first glance. You're probably not. It probably actually took much, much longer to write than it takes to read. So here we also, we can basically say if the sum ended up being smaller than A, and we're just assuming that we're adding 3 positive numbers together here. So if it overflows the whole byte itself, then it will be smaller in the end, and we'll know that this actually we need to carry. Anyway, so we set flags like this. Here, just assigning the value back to the accumulator at the end, and then here, based on the addressing mode, we're going to add certain numbers of cycles. So this just corresponds directly with this table here. So if we have an immediate, we have 2 cycles. If we have a 0 page, we have 3, and if we have a 0 page absolute x or absolute y, then we have 4. But that's not the whole story, right? Because here you can see that it says if a page is crossed, then there's actually an extra clock cycle involved, and I don't have that right now. And it is important to do this emulation properly. You need to be cycle accurate, because there are a bunch of things which are based on timing of cycles and counting clock cycles, especially to do with rendering. And so to get those things right, you need to be cycle accurate. So this is the goal now. After I think roughly 40 minutes of me talking. 49 minutes. Wow, we've got 10 minutes to implement this feature. If the page is crossed, then we need to add the clock cycle. What does that even mean? I think, I could be wrong here, but I think what that means is memory split up into pages. So we have, let's say we have addresses like this. We've got 0, 0, then we've got, put it down here. Let's say we have 100, and then we have 200. These are all hex values, of course. And they go on like this. And then, of course, between each of these, you have 256 bits. between each of these. And each of these is considered a page. So you can think of the 16 bits you have being split up into the 2 bytes. And the most significant byte, the leftmost byte, shouldn't think of it as left and right because of endianness, but here in this description, the leftmost byte we have of the address, that's what we could call the page. So that's why this is the 0 page, because these first 256 bits values are the 0 page. And then this is, I don't know what you would call it then, the 1th page or the 1 page, I guess. Yeah, that would make more sense. And then you have the 2 page. I guess, I would think of this as the 2nd page, although it's actually the 3rd page. And yeah, it's sort of like naming centuries here. It gets a bit tricky. But this is what pages are. And so this idea of having to add an extra clock cycle is basically if we were like reading a value, or so let's go back to these addressing modes. And like absolute X. What I'm going to do is, let's put that here on the side. And let's go to the absolute X decode here, addressing mode. So what we're doing here is we have to do two reads, right? We have to read the program counter here, and then we have to get the most significant byte of it by reading the program counter at the next location. This is a little endian system, so the byte order is actually reversed. So the first byte that you have is the lowest byte, it's the smallest byte, and then the next byte has to be shifted in order to be represented. So what we do is we read the program counter one more address across, and this is where this byte boundary thing can happen, because if the program counter at this point was equal to, let's say, 21FF, we're going to read 21FF, and then when we come to do, PC plus 1, we're going to then go to 2200, and we're going to cross the page. So we need to recognize that, and at this point at this moment in the addressing mode, we'll already add a cycle for that. So if we see that happening, we're just going to add a cycle. And it should be quite straightforward to do that, I think. So we just need to look at the program counter and check if it's FF, basically. That's it. The lower 8 bits, the least significant 8 bits are FF, and we need to do that for all the addressing modes where this might happen, basically. So if the PC ended with OXFF, just so, because this is a 16-bit number, of course, it's got 4 nibbles. We want to take the first 2 nibbles, the byte. We want to check, is that actually equal to FF? And if it is, we're going to say cycles plus plus. Yep, that's it. And I'm just going to put that on its own line to keep things nice and small. All right, that should be it, I think. Yeah. Someone will tell me if I'm wrong, but I'm pretty sure that's what we have to do here. So let's take a look. Let's take a look at what instructions this can happen with. It can basically happen with any instructions that use indexing, and we'll also need to check if it can happen with the indirect instruction itself, because you do need to read 2 values there, so it will probably also happen. Basically any place where we need to read 2. But it's interesting because the absolute absolute instructions contain a full 16-bit address to identify the target location. So I would think that this could also happen, right? That you could cross a page, and I'm wondering why you wouldn't need to add an extra cycle if you cross the page here versus if you cross a page. It could very well be to do with just how the instruction decoding works, like in the logic, because it can very well be that if you think about the AND gates and the OR gates and all of that kind of stuff that the numbers are represented by, it could be that some instruction decoding takes place and those bits immediately flow into some, I don't know, I actually don't know how it works, so maybe I shouldn't even speculate about it. But yeah, I'm gonna double check that. So I'm gonna double check where this extra cycle. So I'm probably gonna try and look that up in the NES wiki. But for now, I'm just gonna implement it in the places that I know I need to implement it in. And my assumption now is that I can just do this in the addressing mode code, that I don't actually have to do this in the instruction code itself. I don't think this changes between instructions. Let's just try and find another place where absolute is used. No page boundary cross here. Absolute, no page boundary cross. Here, that's interesting. Oh, okay, so this actually, it looks like it is instruction based. Relative. +1 if the branch succeeds, and +2 if there's a new page. Okay, so that's a spanner in the works, but no worries. Just means we need to move that code a little bit. Although it does actually, we're gonna need to write code in both places, and this is why, because the addressing mode, it overwrites the program counter variable. So we're writing here to the program counter, and then we +1 to it, we +2 to it here. So we're overwriting the information. Like by the time we get to the instruction, because remember that the way these work is that first the addressing mode code runs, and then the instruction code runs. So we actually won't know if we've overflowed, not overflowed a page, but if we've crossed a page boundary. But this is fine. What we can do is we can go back to the class, and you can see here that we have a bunch of private variables which are basically set during the course of the instruction. And we can just add one more. We have to use uint8t because you could think, right, oh, you only need 1 bit to store this, but at the in the processor level, you're given a smallest value, and that is the 8-bit byte. This is going to be page boundary crossed. I need to constrain this to roughly an hour because my hands are actually freezing where I am here in the attic, and I'm not sure how effectively I'll be able to type if I keep going. All right, so we're gonna write to this page boundary crossed. We're also going to reset it every time we write an instruction. So in our implementation of the CPU, let me, as the first thing, come up here. So here we reset the cycles. Let's also reset the page boundary crossed, which set it to 0. So 0 will represent no cross, and 1 will represent we crossed. Okay, and then in each instruction that could cross a boundary, we're going to set that up. So this instruction cannot. Relative, I believe, cannot. No. But here, I just saw an instruction that was referring to relative mode. If the branch succeeds. Oh, this is if the branch is to a new page. Ah, that's interesting. So if the current address is different, it was on a different page to where, that makes sense. That makes sense. Okay, so that's interesting. So that's even a completely different kind of check. That's going to purely happen in the function, and it's not going to be done through this page boundary crossed. So maybe I should rename that variable, because page boundary crossed basically what we're talking about is during instruction decode, during the place where we, yeah, okay, I think it's fair to say instruction decode, where we look at the instruction mode and we basically pull some values from memory based on that. We're talking about those kind of page boundary crosses. Maybe it's actually fine. I'm going to leave it like that for now, and if it seems like there might be more surprises like this. As you can see, by the way, I don't actually know everything about this processor ahead of time. I'm really learning as I'm going. I'm very much enjoying learning as I'm going. But yeah, so it's very possible that I'm doing some things wrong, and maybe you've spotted something in the code already. Please leave a comment. If you see anything wrong, let me know. Alright, so let's go back. Relative, ignore for now. Absolute. Here we can cross a page boundary, for sure. Whether or not it makes a difference, I don't know. We'll find out. But here, we're just going to say that the page boundary crossed equals 1. That's it. I don't want a line between each of these. And then we can just paste this line of code in every place where that might happen. So it can happen in the X. It can, of course, happen in the Y, because we're reading 2. It can happen in the indirect. So I didn't check that yet, but I'm fairly certain it can happen, since we're reading 2 page boundary, 2 potential instructions. Here it can happen, and here it can happen. And it can't happen, so that is the beginning of the instructions here. It can't happen in the implied. The implied does nothing except for set the actual addressing mode here. Can't happen in the accumulator because, of course, we're just like grabbing the current value of the accumulator. It can only happen in places that we look into memory, and it can only happen in places that we look twice. All right, so I think we've got it covered. We should know at this point in any given instruction what we need to do. So let's go to the beginning of the instructions, which start here. And the nice thing is that we already have a switch case set up for the... we already have this switch case set up, so we'll just add to this. And I think, of course, now we're getting to the point where we have multiple potential instructions happening, and we have to do an if check. Then I think I might actually just break some of these out onto multiple lines. All right, so what we got, absolute X is a +1 if the page boundary is crossed. So I think that's going to be the same for X, Y. It's going to be the same for X and Y. So okay, I'm using switch case fall through, which is, I mean, it's it's not the best practice, but it does mean that when this gets turned into code on the teensy, which, to be fair, is such a beastly microcontroller that you really don't need to worry too much about your resources, like you don't have to scrimp a byte here and there. But that's basically what I was doing here by having a switch case with fall through. Although you shouldn't try and be smarter than the compiler, and the compiler will probably do whatever it wants to do with that. So we've got this absolute X, and we basically want to say, okay, if we cross the page boundary, then even add another one to cycles. Let's actually we can put that on one line. All right, we need the same thing here. On the absolute Y, we count the same number of extra clock cycles. And for whatever reason, with indirect X, I might actually just do a quick Google search, because it does seem strange to me that this doesn't happen with indirect X. Unless I've misunderstood the indirect X addressing mode, it seems strange to me that it wouldn't happen. But I'm very open to being wrong. So 6502 addressing mode page boundary cycles. That will probably be enough information. At least it would be enough information for Google. I don't know if it would be enough information for DuckDuckGo. All right, so Okay, this is maybe not going to be... Alright, this doesn't look like it's quite the same. Doesn't look like it's quite the same thing. Is it possible to procedurally determine the number of clock cycles? All indexed 0-page instructions take full cycle. Let's see what they're saying here. Yes, all of this are written star. This 6th step is also not really what this other page says. Oh, it's the beginning of the rabbit hole there. So what this one is saying is if page crossed. I mean, maybe I've misunderstood what this if page crossed. I wonder if this is actually maybe elaborated on somewhere on this page. I think it's only used like this. Yeah. I wonder if we can find something about it on the NES Dev, which is an amazing resource, by the way. I've seen that, yeah, at the moment I've only looked into these pages, but I've been on this website in the past and just read various things. Cycle reference chart, that's for the PPU. This is going to be important later, and this is actually a big part of why cycles are important. You can see here total number of CPU cycles per frame. And you end up with an exact number of clock cycles, so this actually tells you your timing for rendering. And it will have implications in other ways. CPU, addressing modes. Let's see here if we have something, page boundary. I don't see the boundary. Here we have this cycles is plus 4 plus or 5 plus. Index addressing. I didn't even see these. Should double check to make sure that what I have is actually the same here. I think it is. Something multiplied by 256 here. To check. Really have to check what I'm... Oh, is that the shift part? That's probably where the shift's happening. It looks like a frozen. I'm only reading a information sheet, so probably you don't need to see my face in a high frame rate. 0 page, other addressing. What do we have? Addressing modes and instruction timings are the same as the standards. This page summarizes. No, so it's not really there. Check the instructions page. The unofficial opcodes, that's very interesting to read. Delay code. That's pretty cool. There's probably some tool to work out how to create a fixed delay with minimum code. So trade-off. Really wonder what's happening with the camera. Tick-by-tick breakdown of instructions. That would actually probably be pretty useful just to read in general. And the Visual 6502, this is actually what I was referring to as this, like... here, if you see the 6502, it has this, like, this is a transistor level simulator of the 6502. It's really, really crazy. You know, you can, like, let's step here forward. You can see what is electrically activated at different points, which is just, and these are like the pinouts or pin-ins around. So these are the actual pins of the chip around the edge, and you can see what is getting like electrically activated at different points, all the way down. I don't know if I can like zoom in here, or like you can also run it just at a given point. It seems to be measured in half cycles, and I'm assuming that's because you have the rising and the falling edge of the clock. So the clock is of course just an electrical signal that goes from like 0 to 5 volts, let's say. I don't know what the exact voltage inside the chip is, but you can respond on the rising edge of that clock, so when the clock goes from 0 to 1, and you can respond on the falling edge of the clock when the clock actually goes back down from 1 to 0. And I suppose that's why things are done in half cycles here. That would make the most sense to me anyway. Well, that's that's an interesting one. So I'm not sure. I'm going to have to do some intense Googling, I think, to figure this out. This page so far has been a pretty good. I'm pretty sure I also got linked to this page from the NES Dev Wiki. This has been a pretty good resource so far. But yeah, I need to figure out what's going on here. I think for now, I'm going to assume we're talking about page boundaries in the way that I've understood it. I'm going to have to assume that I'm talking about page boundaries and go ahead in that way. All right, so in this case, with the indirect Y, but not with the indirect X, with the indirect Y, we need to check the page boundary was crossed. And so I'll copy that. And before it was 5 cycles, so I'll change that to 5, and maybe it's 6 cycles based on the page boundary. Nice, so this switch statement gets nice and chunky for each of these instructions. All right, so what else do we have? We've got the logical AND. That basically is going to have the same, I believe that even has exactly the same timing table. So what I might just do is just copy the entire switch statement and just paste it here in place. And then we have the arithmetic left shift. That doesn't have any changes. Here, this branch if clear carry, carry clear, an extra cycle, and a 2 if we're on a different page. So actually this is also easy to check, but we have to check it in a different way. So what we can do is, this is always going to be if the branch succeeds, right? You don't have to check that based on something else. All right, so what we're going to say is if, let's do it before we have to do it actually before we change the program counter. So if the current value, so this is, no, of course it's not going to work. All right, I think the simplest way is let's keep track of what the program counter was before. So just UN16T old PC, and then we change the program counter, and then we can just take a look at it here. We'll say if the program counter, and we need to snip off the bottom byte, so we'll just AND it with FF00. If it's not equal to the old program counter with the same operation applied, snipping off OX FF00, then that means that we need to add an extra 2 cycles, I believe. Was it 2 cycles? Oh no, so it's 1 if the branch succeeds, plus 2 if it's a new page. So I think these are mutually exclusive. So we either add 1 or 2. We don't add both. So we can write it, cycles plus equals 2, and then we can have an else and do that in the else condition. My guess is that going to be that we can do that for all of these branch if kind of instructions. I'm guessing it's going to be the same. I'll assert that by checking this as well. Yeah, so branch if carry set, branch if equal. So all of these branch instructions get the same treatment. Is this correct now? Oh yeah, so it's always 2 cycles in the beginning. It's always, no matter what, it's 2 cycles. Oh yeah, of course we actually have to keep track of the old program counter as well. So that's branch of equal, I need to do that here as well. Then bit is a different instruction, so we need to check if something different needs to happen there. Nope. Then we have branch of minus, so we go back to these are alphabetically laid out, which means that we're not, implementing things for the same group of instructions, but it is a little bit easier to find them when you're looking them up. So we keep track of the program counter in this place. Maybe it would actually be nicer to do this as a ternary. I think it would read a little bit nicer, so we'll just modify that plus equals. And then that, oh. Yeah, I think that's probably a little bit cleaner. So that's that one. My hands are very cold at this point. So I think we'll call it quits after a few of these. But I think at least it's kind of clear now. And I hope you've learned something interesting about this processor too. Yeah, so we need, for branch not equal, we need to grab the old and cycles. Branch if, I really want to remember what this BPL is because it's branch if positive, yeah, the L just comes from nowhere, the L is nothing. So it's going to be the same thing here. We're going to need to, let's take that one out, that would be a bug. So the old program counter, maybe it's something for later, but maybe it'd be worth also keeping track of what the program counter was before decoding the addressing mode. No, that's not necessary. These are the instructions where we're taking branches, so it doesn't even make sense. Here, we get rid of that one. Break, I assume, has no different cycles. It just always takes 7 cycles. I think 7 is the maximum number of clock cycles that any instruction can take. And what's happening is that the break instruction just sort of does a bunch of, I don't know exactly what it's doing, but it basically wastes all of those possible cycles. Then we have the branch, we have another branching instruction below that, so we can do again the same thing. There's a lot of this kind of repetitive copy-paste kind of coding when you're implementing these emulators, I've found in my experience. A lot of stuff is just very slight variations on the same ideas. And it's really tempting to come in and try and optimize everything away with a function or something. And it doesn't, I actually think it doesn't end up being that useful in the end until you really, really know what is the good abstraction. So CLC does nothing. None of these clearing. These are all clear flags. All of these CL or CL instructions. They all clear a flag in the status register. So they just purely have to write something into a register, which takes 2 cycles every time. Then we have compare. Compare does have these page crossed situations going on, so then we need to write into the tables again. So I'm going to go back and no, I'm all the way in the addressing modes now. I'm going to go back here and grab one of these. So we get all the way down to compare, and we need to, on absolute X, so it's 6 cycles, and an extra one if we cross a boundary. Huh? Oh wow, I have this, so that's not correct. That should be 4, I believe. What's going on here? So it's with the indirect I got to 6, and somehow, well, found a bug there. It also means that I can't, I need to be a bit careful with how I'm doing this now. Trying to hold on to that last little bit of fall through that I can here, but I think it's maybe better to just get rid of all of it. Alright, so if we have an absolute X, we have 4 clock cycles and an extra one. Same with Y. So let's copy this and not get that 6 in there again. 4 cycles. Indirect, always 6. Oh, I guess that makes sense then. So like it's 6 because like this one is like maybe using one of his extra clock cycles to do the page stuff, but this one sort of is always going to waste that clock cycle anyway, so it sort of doesn't end up for whatever reason. I am going to figure this out, and I'll share why it happens, but it's pretty interesting. All right, and then we've got, in the end, we've got a 5. So paste that out, and then that's a 5. All right, table is uglier, but it's more accurate, so that's better. And then we have a couple more compare instructions, but these ones, they don't work on as many different kinds. Because they use the X register, it's another really interesting thing that you'll see if you start implementing this. Any instructions that are using like a particular register, they either won't have this like indexing-based addressing modes, or they will have it, but they won't have their corresponding one. So a compare X, even though it doesn't have this addressing mode, it would never have an addressing mode that used X as well. It would only have one that uses Y. And the other way around for Y. Okay, so same for Y. Decrement always takes the same number of clock cycles. Again, this one takes the maximum number. Here we've got some more. So the exclusive OR actually has the same table as add with carry and with or and with and. Yeah, and interestingly, on this architecture, that it was still called E-OR, like exclusive OR, not going straight for the X, but instead using the E, which is kind of funny. Kind of like that. Although it's weird if you're not used to seeing it, that you get this exclusive OR with an E. Okay, so then we get some more. We get increments, nothing changes. Inc X, nothing changes. Y, jump. So we have indirect addressing, but it doesn't actually affect it. Jump to subroutine. We've got load accumulator. So this is the first load instruction. This is basically move for corresponding with the VM. And it looks to me like this even has the same page layout as well. So we have an immediate 2, 0, page 3, 4, 4, 4, 4, 6, and 5. I believe that's actually just the same as this. So 2, 3, 4, 4. Yeah, another bug. So actually I need to go and fix that, these other places. 4. This might be a place, you know, where it's worth putting a function, like writing a function and doing it there. Because C++ has another cool feature, which I kind of wish JavaScript had as well, but of course it's not this kind of language, so it doesn't have it. But you can do inlining by giving the compiler some hints. And inlining is basically where it will take something that's written as a function with, like, you know, inputs and outputs and arguments and return values, and it will inline it. So actually, like, you know, the compiler will pull it apart and basically just cut and paste the code of that function just into your body. And of course, what that means is that any places that you use that function, instead of you having less program space because you only have to talk about that function once, you end up, you know, sort of expanding it out in all of those different places. But you get the benefit of not having a call stack invocation. So yeah, that might be something worth looking at, and it's definitely proving itself that trying to live with these fall throughs is not a good idea. All right, so I think I have this one correct now, so I could probably just go and reapply this. So exclusive or... where else would I have had that? I had it in AND, of course. So there are my bugs there in AND. Yeah, they would all inherit this extra cycle behavior if I didn't do this, which would be wrong. So it's AND, and then this is add with carry, which also gets it. Good progress. Here I fixed it. A weird sound from my boiler. Let's check that that's working. Yeah. Alright, so where are we at? We're at load accumulator, and that had the same table, so we can paste that in here. I'm pretty sure it's the same, right? Immediate 2, 3, 4, 4, 4, 4, 6, 5, 2, 3, 4, 4, 4, 4, 5, and 6. Yeah, correct. And it has those page boundaries in the same place. The load X is slightly different. It only has something different for the absolute Y. So let's borrow that piece of code. The load X. Yeah. Here, I will come back in my own time and make sure that I fill in all of these fall through cases, because they're just, you know, as nice as they are, they're not worth it now. I assume we're going to have the same thing in the Y case, and you'll see that, you know, we're talking about loading the X here, and we only have an absolute Y, and you'll see that in the Y version of this instruction, we have only the X's instead. So put that here. Load X, load Y. Logical shift, nothing changes. Then we get OR, so that it's not exclusive OR anymore, it's just OR. For some reason we put an A. All the mnemonics have 3 characters, and sometimes I think they just threw a dartboard, you know, threw a dartboard with some letters on it and just chose a letter based on that. There probably is actually a reason. So the table in load A was the same as the ones in XOR. So we can use it here in OR as well. You can see how instruction decoding also plays into this, because there is so much commonality between these instructions. Of course, only the actual operation itself changing and the flags which are set, which you have to do complicated looking stuff in here when you're emulating, but when you're actually dealing with electrical wires and logic gates, these flags were really, really easy to calculate, because you're basically just, wiring one output of a wire to your writing a flag. Ends up being really much easier in hardware to assess these flags. Okay, so that was OR. We've got the pushes, nothing changed. This is push the status register. This is pull. They use the terminology pull instead of pop, which is quite cute. Nothing changes here. Nothing changes here. We have subtract with carry. That has the same kind of flag setting as all of these other addition or logical operations have. So we've got subtract with carry. So let's replace its table. Then we have some flag setting instructions. We have the store instructions, which don't seem to have any changes. So that's it. That's actually all the instructions and this extra cycle taken care of. So now that's built in, and in true, in the right way of doing things, I will make a little commit with this as well. And I sort of messed up Git yesterday when I moved my Git folder around, and I didn't mess up Git, but VS Code got confused. So I don't want to do any of these things. I actually changed the make file around a bit, but we want to commit here the CPU. Actually, I'll commit the make file stuff first, because that's just something something I'd already done. The make file and then the main CPP. I think I just commented out the Arduino stuff so I could run this locally without. I haven't learned enough about makefile yet to be able to point it to the directory where the Arduino headers are. So that's another learning experience that I'm going through at the moment, is using makefiles. But I'm also quite impressed with makefile as an idea, despite the tab stuff, which I don't get. But I think makefile just separately is a very cool system, and I might do a video about that one day, like building the way it works. It's got a really smart mechanism, which I'm also sort of surprised that it works, because it's based on timestamps. I'm surprised that it works as well as it does, but it does. Okay, so this was a change in the CPU and the VGA file. I moved it, but I think I never committed that in the first place. So, all right, so I'll do a commit message here on the command line. Git commit. And we'll say improve makefile. It was an improvement. Found some stuff about how to make it generic and how to separate all of my different concerns and names and things. All right, that's the makefile stuff. And then we just want to commit these changes made here in the CPU and the CPU header. So git commit message. And so what do I want to... so basically what's been done here has been add page boundary. I hope I'm spelling boundary right. I'm really bad at spelling. It often comes through in these things. Page boundary cycle checks. Page that's a nice way of writing this. Page boundary cycle accuracy to the CPU. Very nice. And I will push that. NES, although then no deployments will be triggered by that. All right, and if you want to follow along with this project as it happens, I don't know how much I'll be continuing with this, considering some of the upcoming changes I have in my life soon. But yes, you can find it here on my GitHub. So Francis R. Stokes on GitHub. And then one of my most recent projects is the teensy NES. So that's here. Hey, thanks for watching. Thanks for joining me today in this this slightly unorthodox low-level JavaScript or low-level C++, regular level C++. I don't know. This episode, and yeah, I'll see you next time. Bye.